What's up, everybody? Welcome back. Today we're going to be working on part D of Fluid Mechanics Problem 3. And our question today, or our problem today, is to derive an expression relating torque, angular velocity, gap width, bob height, and bob radius of a Couette viscometer to fluid viscosity. I've gone ahead and drawn us a Couette viscometer here. It consists of two concentric barrels, which are then filled, the gap is filled with fluid. You apply a torque to the handle of the viscometer, and it helps you visualize the velocity profile between the two surfaces. Okay, just to label a few things on our drawing that we have here in the question, we have the radius R, okay, we have the height H, we have the gap width D, exists there between the barrels. We have a torque applied to the handle, and some angular velocity, omega. I think that's all we need. Oh, and then fluid viscosity is designated by the Greek letter mu. Okay, I think we can see everything up there. All right, so let's talk about our velocity profile first of all. So between two surfaces, assuming a no-slip boundary condition, if this surface is moving relative to this surface, we will see a laminar velocity profile that's linear, meaning as you move farther away from the surface, the velocity of the fluid with respect to the surface becomes greater. Okay? And we refer to these terms as our shear stress and our shear rate. Okay? Our shear stress, excuse me. When I defined torque up here, we're going to use, there's going to be a lot of T's here. We're going to use this symbol for torque, tau symbol, and then for shear stress, we'll use this T. Okay, so for shear stress, we're used to this. We have force over area. And then we have our shear rate, sigma, which is equal to the laminar velocity profile's slope here. The change in velocity in this direction with respect to a change in distance in the y direction. Okay. Interestingly enough, our shear stress is also equal to the fluid's viscosity, absolute viscosity, times the shear rate. Okay. And so we'll use that here in just a moment. Okay. So torque. Let's talk about torque. Torque, as we know it, is equal to force distributed at a certain radius away from a hinge point. Okay, so like when you're opening a door, you put a force on a handle that creates a torque along the length of the door, which opens the door. In the same way, we have that here, right? So our torque is equal to the force we apply times the radius. Now, the other thing that we have is we have this information here. So let's go ahead and start tying these all together. Well, force we can relate to the shear stress and the area of the fluid. Right, so we have shear stress times area times radius. And the area here is the contact area between the cylinder, the interior cylinder, and the surface, or the fluid, excuse me. So that becomes the circumference of the barrel times the height of the barrel. Right? So we get shear stress times 2 pi r times the height and then times r again, squared. Okay, and that's all equal to our torque, tau. Okay, and we also know that our torque right here is equal to, or not, I'm sorry, there's too many t's on the board. Our shear stress, T here, equals mu times sigma, or our fluid viscosity times our shear rate, right? So we have now torque equals this guy, which is mu sigma times 2 pi r squared h. Okay, we're almost there. Let's just talk briefly about what sigma is. So we said sigma was dV dy. We have better terms to describe it in, shown by our picture. Okay, so dvx, our velocity. So that's linear velocity. We're not traveling with linear velocity here. As we rotate our viscometer, we have an angular velocity, right? If you recall from physics, your linear velocity is equal to your angular velocity omega times radius r. Okay. And then our change in y, we're not really changing height per se, but we are changing in gap distance. We have a distance d between. So we can rewrite this as omega r over d. Okay, so let's go ahead and do that. We have now omega r over d. You can see that's our change, our slope of our velocity profile, right? Assuming a linear velocity profile with no slip condition, no slip boundary, times 2 pi r squared h. Okay, and then lastly, let's just make sure it's pretty clear that we're trying to relate these things to the fluid viscosity mu. So we're going to separate everything from mu. So we have mu is equal to tau d over 2 pi, we have an r cubed, and then an omega and h. Okay, and I think that's it. This is a short one today, guys. Just a quick derivation. And we've shown the relationship now between our fluid viscosity, so got that one, radius, angular velocity, height, gap width d, and torque. Okay, so that's everything. We got it. Thanks for joining me on this problem, and we'll see you next time for another fluid mechanics problem. Thanks. Bye.